power A, where P for A is the highest power of P that divides A. Okay, and this is something that people study, and this is called a Steinhaus random multiplicative function. Okay, so it's a Steinhaus random function because it's built from these Steinhaus random variables. And it's multiplicative because you can see that the value n is built multiplicatively for the values at products. And actually, it's totally multiplicative, just like a character is totally multiplicative. And in this setting, there's a conjecture of Helson from 2010, which is if you look at the L1 norm, so here the L1 norm is just this expectation of the absolute value, this should be little o of square root x as x tends to infinity. Okay, now we don't know how to go about proving this. No upper bounds were better than square root x. There were some lower bounds, so the lower bounds Helson himself, following from his work, and of von Rankel and Seip, and of myself and Bali and Ranzigol. And we showed that the expectation is at least as big as root x over log of x cubed. So if the conjecture is true, it's at least not very true. It can't be too much more than root x. But nothing was known about how to maybe prove this, but at least in this setting there was a conjecture that it should be square root x. I should say as well, why did Helson think this? Well, maybe this is analogous to the following. So what I'm doing there is I'm taking a multiplicative character, a random character, and summing up to some point, and taking the L1 norm. And what he suggested is maybe this is analogous to taking an additive character and summing up to some point, and taking the L1 norm. And if it is, then this is the L1 norm of the Dirichlet kernel, so this is actually really small. This is maybe like log x in size. So in this setting, it's definitely true that this is log x. It's not clear that that should motivate you to believe the conjecture, but anyway, that's a reason. I'll state one more reason why you might think that square root x isn't sharp. So what we've been doing here is we've been looking at problem on the 0 line. Okay, so we've taken the coefficients of the L function, the L function, and summed them up without taking limits. And what you can think about is what goes on the 1/2 line instead. So we look at 1 over r minus 1, the sum over chi mod r, L1/2 pi, the absolute value, which roughly speaking is the same as 1 over r minus 1, the sum over chi mod r, the sum over n up to about r, chi of n over square root n. Okay, and now, so if what we're going on was square root cancellation, then what we'd expect is that this should be like the square root of the sum of the squares. So this should be like the square root sum over n less than r, 1 over n, which is like square root log r. So square root cancellation suggests that's the answer, but that's not the answer. So actually, it's order log r to the power 1 quarter. And this is a result of the gap. And the standard margin for the lower bound and the Heath Brown for the upper bound. Okay, so on 1/2 line, at the critical point, you get better than square root cancellation. And why is that? Okay, I stand corrected. Thank you. Right, so why is it smaller? So this is because the role with the order product. Okay, so on the 1/2 line, even though the order product certainly doesn't converge anymore, it still has a big influence on the behavior of the L function, and the order product causes a sort of collapse. So you have a collapse in the size to the order product, which gives you this size for the small ones. So you can think about the question, do we have square root x or better than square root x for the L1 order character sum, as being a question, does the influence of the order product extend even out to the 0 line, or not? Right, so now I will put you out of your suspense, or misery, such as it was, right, and state some theorems. So theorem 1 is in the random setting, so there, be a Steinhaus random multiplicative function. x over square root log x to the q. So this means it's at most some constant, depending on q times this, and it's at least some other constant, depending on q times this quantity. Right, so in particular, if you take q equals 1/2, and you get that the 1 norm is like square root x over log of x to the 1/4. So the conjecture of Helsing is correct. It is with log of square root x. It's x tends to infinity. So now you can ask, so what does this mean for the character sum? So maybe this means that for the character sum problem we should have less than square root cancellation as well. Or maybe the random model is just failing to capture the arithmetic in the character sum problem properly. And we know that has to be the case to some extent because I already showed you that for a certain range of x, x is order r, essentially you do have square root cancellation, and not less than square root cancellation. But it turns out that that's essentially the only case where you don't have less than square root cancellation. So this is 2, so let's r be large prime, and x will be 1 and r, 4. We'll set L to be the minimum of x and r of x. And then for any q bigger than 0 and strictly less than 1, we get an upper bound. Actually, it doesn't matter. So it's not quite what r. Q is less than depending on q x over the minimum of square root log L and square root log r to the q. So provided that x tends to infinity and r over x tends to infinity, the denominator tends to infinity. So you have a less than square root segment. So probably the second term, so the square root log r can be removed. And this is work in progress to do that. I think it can be, but I haven't checked all the details yet. And if it were removed, then presumably in view of theorem 1, that would be a sharp bound. So if you don't immediately see why L should come into things, I'll explain that in the last part of the talk. But maybe if you've worked on these things before, it's reasonably clear there should be some symmetry between x and r over x. Right, so that's the end of the introduction. Should I have questions before I go on and talk about the proofs? Here? So if I, so another way of saying that would be if you apply Cauchy-Schwarz to get to the second moment and just expand out and use orthogonality, that's what you get. That's the answer. So the second moment is like log r. So if you do Cauchy-Schwarz, you get square root log r as a band for the first moment. No, for the character you get this by orthogonality. Yes. So what I'm saying is that the Cauchy-Schwarz band, which uses the orthogonality, so that the second moment comes from orthogonality, the same for the characters as for the random case. And what I'm saying is that the Cauchy-Schwarz for the second moment band is incorrect for the first moment. And it's also incorrect, although not as much, for the character sum as well. Thank you. Other questions? Right. So I want to say a bit about the proofs. So the proofs are quite complicated, so I'm not going to give even a sort of detailed sketch of how they work. What I want to do instead is to just identify some of the issues that come up and how you might start to think about trying to solve the problem. So first of all, I'm only going to talk so I'm talking about the random case here, of theorem 1. And the first sort of idea, or theme, so theme 1, I want to connect this thing I'm trying to bound to the order product, which in this case is a random order product. For S, order product over primes less than x, 1 minus f of b, p3s to the minus 1. Why do I want to do that? Well, actually, there are lots of reasons. So, first of all, it's the only is twice an natural number, I can expand the square to do something. If the exponent isn't twice a natural number, I can't do that, so it's much less clear how to proceed. But if I can get down to the order product, then I'm much happier, because if I have an exponent 2q up here somewhere, it passes through the order product very nicely, so I just get exponent 2q here, and if I write this as an exponential, it just becomes a 2q as a coefficient exponential. So I'm much happier handling fractional powers, or not twice integer powers, with products than with sums. So that's one reason. Another reason, so in the order product, these terms, 1 minus f of p over p of s to the minus 1, are independent, which is always good. Yes. Yes, thank you. Yes. Right. So in the order product, these things are independent, which is good, whereas in the original sum, the independent f of p's are all sort of tangled up, making up the f of n's, which is much harder. And then the third reason is, I already told you, so on the 1/2 line, the order product is responsible for the drop in size, as compared with square root cancellation. So I told you we're going to have a drop in size here as well, so maybe the order product is going to be a useful thing to have around. So I said, so the size of the first moment is smaller than you'd expect just from square root cancellation. The reason it's smaller is because this thing doesn't behave like this sum, it behaves like the order product instead. But it doesn't converge, it still governs the size, despite not converging. So it requires a lot of work to see that it still governs the size, but heuristically that's why this is the size. If you pretend that this is like a random order product, this is the answer you get. If you pretend it's like a random sum, this is the answer you would get, which is true. Okay, other questions? Right. So I want to get the order product into play. How can I do it? So the obvious way is to use Coulomb. Okay, so f of n is like 1 over 2 pi I, the integral up a line. And f is a finite product, so I can have any positive abscissa from the two. But this won't work, so why not? So this is inefficient. Well, first of all, you have this 1 over s around, which isn't very good, because I'm probably going to end up putting some absolute values inside the integral at some point. And then I'll have something like integral 1 over mod s, which diverges logarithmically. And that's a disaster, because I'm trying to win square root log x most, so if I lose a log, I'm done. Now you could fix this if you're happy with having a smoothly cut sum instead of a sharp cut one here, which you might be. But then there's a much worse problem. So first of all, that diverges logarithmically. Also, we would need to get cancellation from the oscillations of f of s times x to the it, which is generally very hard. Okay, so if I took c to be 1/2, which is the most natural choice, then I'd have an x to the 1/2 here, which would come out, and that would give me x to the q in the answer. I take the 2qth moment. And then I'd be left with an integral, and what I'd be trying to show about the integral is not that it's smaller than a small power of a log, or even that it's bounded. I'd be trying to show it's actually small. It's going to 0 like 1 over root log x. So to possibly do that, I need to show that there was lots of cancellation going on in these guys, which is very hard. So we'll say just a little bit about another way of proceeding. So instead, we'll let p of n be the largest prime factor of n. And what I can do is I can decompose my sum according to the size of p of n. So I'll split it up to the numbers n, where p of n is at most x e to the minus k, and at least x e to the minus k plus 1. And then I can split up this sum, so every number here has at least one prime factor on this range, and none which are bigger. So I can split these numbers up into the piece which has all of its prime factors on this range, and the piece which has prime factors smaller than this. And since f is multiplicative, when I do that, f will split up over these two sums. Okay, so this is the same thing as the sum over k bigger than 0, the sum over m less than x, such that if p divides m, then p is on that range. M strictly the 1. F of m, and then the other part, so the sum over n less than x over m, n is is x e to the minus k plus 1 smooth. And the important thing to note here is that in this sum, we only have prime factors up to x e to the minus k plus 1. And in this sum, we only have prime factors that are bigger than x e to the minus k plus 1. And those things were chosen independently, so this is independent of this. That's random variable. So I'll come back to that in a minute. So if I hold that, if I have just some coefficients, some numbers, Cm, and we'll call this here I sub k, it's interval. So if Cm are just some numbers, and I'll put what's the expectation of the sum over m with all of its prime factors in I sub k over f of m Cm to the 2q. Well, by Holder, this is at most the expectation of the square of that sum, all to the power q. And then for the square, I can just expand that in usual formality, like usual. So this is the sum over m with all its prime factors in I of k, mod Cm squared to the q. Right, so this is a calculation. And this is true of the Cm as some deterministic numbers, but the point is that since the sum on the inside there is independent of all the randomness on the outside, I can condition on the sums on the inside and treat them as deterministic. Okay, so by conditioning, what's it like here? So I call this double sum here, S sub k, inside there. If I look at the expectation of S sub k to the 2q, I can do the same thing, and I can get that this is at most the expectation of the sum with the prime factor condition. And then just treating the sums up there as deterministic coefficients. So the sum over n less than x over m, n is pretty smooth. F of n squared to the q. Okay, so if you're not used to this, you can just think, since I have this independence, I can freeze the things on the inside, then I can do Holder, like in the deterministic case, then I can re-randomize over the things on the inside. That's what happens. Or I can split the expectation up into the expectation over the inner thing, which is here, and the expectation over the outer sum, which goes away in the Holder application. Right, now, once you get to this point, you then do a few more steps, which I'll just list what they are. So now you can replace the sum over m by integral. Okay, when you do that, you pick up a rate that reflects the density of the set of numbers that you're summing over there. And once you've done that, so you then have inside the bracket, you have an integral of the square of some sums of various points. So an integral of the square of some things looks a lot like the kind of thing you would hope to apply Parseval to, and so forth. And you can do that. So then you can apply suitable form of Parseval. You do that, so on the physical space side, you have the sum of f of n. On the frequency side, you have the Dirichlet series order product, which is what you want. So when you apply Parseval, what you finally get out, so of course I'm omitting lots of stuff here. So you get that this is roughly the same as x to the q times the expectation y log x, short integral, so from minus 1/2 to 1/2, absolute value f of 1/2 plus it squared dt, all to the q. Remember that this is a finite product here. So if you've seen these kind of things before, maybe you can vaguely follow what happens in the steps I skipped. If you haven't, then you're definitely not supposed to be able to follow what happened in the steps that I skipped. The point I want to make is, why does this work? So why does this overcome the problem that I was talking about over there? So there, I have this x to the it around, I need to capture some of its oscillation, and I didn't know how to do that. Here, I use Parseval, and Parseval is no oscillation. Okay, in Parseval you have a mean square of something on one side, and you have a mean square of something on the other side. So there's no oscillation that's been lost, because there's never any oscillation